All right, so let me back up one slide. Remember, we had we had just finished talking about what to deal, how to, if you're given a solution, say you're given a solution with two soluble compounds in it, like silver nitrate, which is soluble, and sodium chloride, which is definitely soluble, and say, give me the complete molecular equation, the molecular equation, the complete ionic equation, and the net equation. Right? So this is one of those cases. This is a double replacement where you can figure out what the products are. It's not always possible, but in this case, you can. You just trade places with these two cations. That one goes over there and this one goes over here. And then your products. And then you look up in the solubility chart that's at the back of the review document and see, is there one of them that's not soluble? Usually is. Sometimes both of them are insoluble. And in fact, the precipitation part of the reaction is what drives the reaction forward. Because when you form that solid, it takes those two, the cation and the anion that forms the solid, removes them from the reaction environment. And that drives the reaction forward. Okay. So we learned how to do that. Okay. Somebody's been using my board. Let's see how far I get with it. Okay, now we're going to pick it up with stoichiometry of these precipitation reactions. How do we assess either how much product we can expect to get from a reaction, or how much of one of the reactants do we need for the reaction to proceed? Either way, it works. Stoichiometry. And the first few steps are essentially the same. You have to write the compounds correctly, right? If the word problem gives the name of the compound, then you've got to be able to write it in symbolic form. Then you put them together in your reaction and figure out what the products are. Okay. Then you balance the equation. And from there, we start to get some deviations. One is, how do you determine the number of moles so that you can move within the equation? Because without moles, you can't do anything. You're stuck. It used to be if you just had mass. That was our first introduction to stoichiometry. If it was just mass, you're stuck unless you can convert to moles. Solutions are the same way. You can't take milliliters of something and go anywhere in the equation unless you find out how many moles of the reactant or product you're dealing with. So in order to do that, we use that relationship, right? Molarity equals moles divided by volume. And if you want to calculate moles, you just solve for the moles, molarity times volume. So usually the reactants are going to be given to you for these solution reactions, given to you in terms of molarity of the solution and how many milliliters there are, or how many liters there are. Then you can calculate the moles, and that's when you can move. Okay, we're going to do some examples. Right, I showed you this one last time. The solubility chart, you know how to use it, correct? All right. Anybody use road maps anymore? With the distance calculators on them? Right, you have where you start, where you're ending up, where they meet. There'll be a number in that box, and that'll be the number of miles. Similar thing. You take the anions down the left-hand side, cations across the top, and you find the two matches, follow them down. If it's clear, soluble. If it's gray, insoluble. Okay. So you don't have to memorize the rules. If you do it enough, the rules just start sinking in anyway. Okay. Well, let's take this example. We're given 10 milliliters of 0.3 molar sodium phosphate and reacted with 20 milliliters of 0.2 molar lead 2 nitrate. And we assume that there's no volume change. We have to assume that, otherwise we're stuck. What typically happens when you put something into solution, say if you put ethanol into water to make some booze, then you're going to, the final volume is going to be different than the summation volume of the two components. Thank you. So in this case, we have to assume that the volume's going to be constant. All right, so we've got sodium phosphate. How do we write sodium phosphate? It's one of our reactants. Sodium, right? How about phosphate? That's a polyatomic ion, right? This is an alkaline metal with a +1 charge. This is a polyatomic ion with a 3- charge. So we have to balance the charges. That means we need 3 of these. 3 pluses equals 1 3-. Okay, so we got that one. And if it's in solution, we know that we can write this. There we go. We've got an aqueous solution of sodium phosphate. That's in one beaker. Then in the other beaker, before we put them together, we've got lead 2 nitrate. So what's lead 2? It's got a 2+ charge. Right? And nitrate is a polyatomic ion with a -1 charge. So how do we balance those charges? Remember, for polyatomics, the charge is distributed over the entire ion. So you can't bust it up. You can't change this to 2 and 6 to make the charge balance. You have to use parentheses and use 2 of them. 2 minuses balances that 2+. Okay. And this is aqueous. We're told it's in solution. This is before we put them together. What we have in these separate beakers is 10 milliliters of 0.3 molar. 0.3 molar. That's given. And 20 milliliters of 0.2 molar. Okay, when we put them together, what's going to happen? Well, first of all, what's going on in these separate solutions? If they're soluble, that cation and that anion are dissociated. They're hydrated in the solution, right? You've got 3 sodiums and 1 phosphate. That's what's actually happening in the solution, right? So when you put the solutions together, these ions have a chance to interact with the ions of this other compound. And the cations associate with the anions, and the anions associate with cations. So this sodium would associate with nitrate to produce one of the possibilities, right? -1 +1. And we look it up in our chart, and we find that sodium nitrate is soluble. Right? So that's not the precipitate. Right? What precipitate will form? So we take this phosphate and we put it together with this lead, right? We already did the sodium and the nitrate. Now we do the lead and the phosphate. So in this case, we get lead with a 2+ and a phosphate with a 3-. How do you balance that one? When you got an odd and an even, you cross multiply. Bring the 3 over here. And the 2 goes over there. We look that one up. We find out it's a solid. That's your precipitate. Okay. So, come on. That's just everything I've said so far. So there's your precipitate. Now that we know that, we can answer the next question. Well, we have to balance the equation first, of course. So we're going to use one of our tricks. We have polyatomic ions in here that remain intact on both the reactant and the product side. So we can use these as balancing units. All right? We have sodium. I'm going to leave the charges off just for convenience. Phosphate, lead, and nitrate. Okay. So on this side, we have 3 sodiums, 1 phosphate, 1 lead, and 2 nitrates. And on this side, we have 1 sodium. So line them up. Phosphate, we have 2. Lead, we have 3. And nitrate, we have 1. So we can see it's unbalanced at this point. So we don't have any single elements in there to hold till last. So sometimes you just start at the beginning, right? If we have 3 sodiums on this side and we want 3 on this side, we use a coefficient, right? That gives us 3 sodiums and 3 nitrates. Okay. Getting warm. Now we've got 1 lead and 3 leads on that side. So if we put a 3 here, that gives us 3 leads and 6 nitrates. Uh-oh. Wait a minute, phosphate. Hold on a second. Let's go Krogering. Let's go back here and let's see. Leave that too. Instead of doing lead, let's do the sodium. We got 3 sodiums here. Well, we got 3 sodiums there. 1 phosphate. 2 phosphates. Oh, okay. So if I need to get 2 phosphates, I want to put a 2 here, right? So that makes 6 sodium, 2 phosphates. And let's see, 3, 2. All right, let's go to lead next. We need 3 leads, right? That gives us 3 leads and 6 nitrates. Oh, okay. Instead of 3 here now, let's put it, make it double. Let's make 6. So that's 6 sodiums and 6 nitrates. 6, 2, 3, 6. Now we're balanced. Okay. Takes practice. And it's a perishable skill. So if I only do it once a semester or once a year teaching it, I have to rewind and get familiar with it again. Okay, so now we've got our balanced equation. Now we can do something with it. Let's get these out of the way so the distraction. There we go. All right. So now we have our balanced equation. And we want to know the moles of reactant and the moles of product. I think we introduced the concept of limiting reactant, didn't we? Yeah, I'm sure we did. When you have 2 or more reactants and you're given absolute amounts of each one, you can be pretty sure that one of them is going to run out. One of them is limiting. So that's where we have to find out which one's limiting next. How many moles of this compound do we have? Well, if we stick to the formula, we're going to change that to liters before we multiply. But I got another trick. If you multiply molarity times milliliters, 0.3 times 10 would be 3.0. Let's see, 3.0. This is millimoles. Okay. And I'll prove it works later. Okay, do the same thing over here. We get 4 millimoles. Okay. Now, which one runs out first? Okay, here are the millimoles and millimoles. There we go. What was the question? What's the mass of the precipitate? So we're looking for the mass over here. And that makes sense because it's a solid, right? It's not in solution. So we have to find out which one is limiting. There are a number of ways you can do this. You can say, if I have 3 millimoles of this, how many millimoles of that do I need? And then do that calculation. But when the question is, how much of a product are you going to get? It usually saves you some time if you say, all right, if I take this and I make that out of it, use all of it, what's the value that I get? And do the same thing with this one. What's the value that I get? Then compare them. The smallest number, the smallest value tells you which one's limiting. So with this 3 millimoles, how many millimoles of lead 2 phosphate will you get? If we have 3 millimoles of this compound, and we want to convert it to millimoles of lead 2 phosphate, right? And we want to cancel this one. We need a conversion factor. So where do we get the conversion factor? From the balanced equation, coefficients. So for every 1 mole of this, it takes 2 moles of that. Okay, so we just need to divide this by 2, and we get 1.5 millimoles, because this cancels, of lead 2 phosphate. Now we'll do the same thing for this one. I usually don't go to the trouble of writing these things all out like this, but for the first time around, so that I don't lose you in the process, I'll just write them all out. All right, so here again, we also need lead 2 phosphate. And we need to cancel this time. Excuse me. My mistake. No, that's right. Lead 2 phosphate. Lead 2 nitrate. There we go. Okay, so moles of this will cancel. How much of this do we have? We have 3 of those. That's the coefficient. And still we have 1 of those. So 3 into 4 is what? 1 1/3 millimoles of that compound. This is the least amount. So that's the limiting one. That makes this one excess, which means we're going to have some of this left over and all of that's going to be gone. But now we have this many millimoles of that compound. So now that we have millimoles of that compound, with a tweak, we can calculate the mass, right? In order to use molar mass, though, it's grams per mole. So we need to turn that into moles. So if we have 1.33, yeah, just carry it on out, millimoles, the way I convert is say, what does milli mean? Milli means 10 to the minus 3. Right? So it's 1.3 times 10 to the minus 3 moles. Now we can convert to grams or moles. We just need the molar mass of Pb3PO4 taken twice. All right, so we need 3 times lead. What's lead? Here, 207.21 grams per mole. Okay. How many phosphates? We have 2 phosphoruses. And it's 30.97. Okay. How many oxygens do we have? 8. So that's our molar mass for that compound. Okay. Alrighty then. Let's see. 207. This is going to be a heavy compound. 3 times. And then 30.97 2 times, and add those together, and then 8 times 16. Put those together. 8, 11, 57 grams per mole. That's because of that right there, lead. That's why lead crystal's so heavy, right? Because they mix in lead to make it shiny. Okay, 8, 11, 57 grams per mole. There we go. Times 1.33 exponent minus 3. So I get, well, a calculator tells me 1.0821 grams. But if we go back and look how many, we only had 2 significant figures, didn't we? Or was this one 3? Did I make a mistake? No, it's 2. 2 molar. Okay. Okay. So the answer might show up as 1.08, but technically it should be 1.1 grams. Only 2 significant figures. Let's see what the slide says. All right, so there's the molar. Well, okay. Molar mass is in, yeah, it says 1.08. 1.1 is correct to the correct significant figures. Did I lose anybody? Or we just blurry on Tuesday morning, Tuesday noon? Okay. While it's up here, we take that same problem and assume no volume change. What's the concentration of nitrate ions left in solution? Notice how many millimoles of nitrate ions did you start with? Well, we had 4 millimoles of the compound, and for every 1 compound, we get 2 nitrates, right? So we actually have 8 millimoles of nitrate ions. And they're all in solution, right? They're all part of this soluble compound. So they're still in solution. What has changed, though? This didn't change, right? We can't create or destroy. And it didn't go into the solid. So they're still floating around. What has changed? Volume. We added 10 mils plus 20 mils. So now the volume is bigger. We got the same number of millimoles of nitrate, but more volume. So if you divide, I'm going to erase this now. And here's where I prove it to you, that millimoles works. If you divide 8.0 millimoles of nitrate, divide the total volume, 10 plus 20 is 30 milliliters. You will get molarity. All right. This is milli. 10 to the minus 3. This is milli, 10 to the minus 3. They cancel. Moles divided by liters is molarity. Okay. So let's see, 8 divided by 30 is 0.2667. 2667 molar. And we can only keep 2. 0.27 molar nitrate. Okay. Oh, there it is. We're just watching to see if I got it right. Okay, here's a trickier problem. We know we got that much nitrate left. We also know which one is excess. This one's excess. So we know there's going to be some phosphate left over in solution. We only use part of it to make this. All right. This was the limiting reactant. Once it ran out, the reaction stops. That means we have some of this left over. So we do have some phosphate ions left. We need to know how many there are so that we can calculate the concentration of phosphate ions in solution. Okay, how many phosphates did we start with? Well, we had 3 millimoles of this compound and only 1 phosphate per compound. So this is what we started with. This is initial. Now we got to find out how many did we use. Well, where did they end up? They ended up over here. 1.333 millimoles, right? All right, this is the millimoles of the compound. How many millimoles of phosphate did we use? 2 times that, correct? Because of that 2 right there. For every one of these, which this represents 1 of this unit, we've actually got 2 phosphates in there. So we got times 2 equals 2.66 millimoles of phosphate that's used. So what we have left over is 3 minus 266. It's 3. Right. 0.3334 millimoles of phosphate remain. Now we can do the calculation the same way we did before. Divided by the total volume. And let's see what that is. Let's see, 0.0113. We're limited, actually, yeah, we're limited to 2 significant figures. So it's 0.011 molar phosphate in solution. Yep. Okay. All right. Now, this discussion centered on double replacement, which is also a precipitation reaction. Now we're going to look at acid-base reactions. And this is a practical approach. How do you deal with acid-base reactions? Next semester, we go into a lot more detail in acids and bases. But for this part of the course, we're only interested in how do they react and how do we use them to do stoichiometry. Okay. We'll hammer this one harder next semester. Okay. When we say acid-base reactions in Bronsted and Lowry, that's a thing that we haven't defined yet. So we're going to give you a little bit of taste of what's coming, by defining a Bronsted-Lowry acid and base. And a Bronsted acid, and I'm going to use this. Okay, it worked. Nope. Dig into my haversack. This is my generic acid. Remember when we were naming compounds, acids always start with a hydrogen, at least one, sometimes two, sometimes three. So this is the part of the acid that could be anything. And this has one, in this case, this is monoprotic. It only has one proton available. This is the proton donor. That's a Bronsted-Lowry acid. Now, if we have something like, say this, we have this part of the molecule and it has a hydroxyl on it. This would be a proton. Oops. Can't spell. Acceptor. Okay. How would it be a proton acceptor? Well, if we put them in a reaction like this and do a double replacement reaction, right? The anion goes with the cation, just like that. Okay. And the proton goes with the anion. HOH. Does that look familiar? That's water. Okay. So the net reaction, the thing that drives the reaction is that proton plus that hydroxyl yields water. That's the net reaction for an acid base. And we're at this point, I think we're just going to focus on strong acids and strong bases. It simplifies things that way. Let me see if this is going to play. Do I have time to do it? How many of these things do I have? Okay. Let's see if it'll play.
Hydrochloric acid contains hydrogen ions and chloride ions in aqueous solution. Sodium hydroxide contains sodium ions and hydroxide ions in aqueous solution. When these two solutions combine, a neutralization reaction takes place. In this reaction, hydrogen ions from the acid and hydroxide ions from the base combine to form water molecules. The sodium and chloride ions are unaffected and remain to form a neutral sodium chloride solution. Neutralization can be summed up by this simple ionic equation.
Okay. There was another teaser in there that we'll get to next semester, where you saw the oxygen with 3 hydrogens attached to it and a plus charge. That's simply because hydrogens don't do this. They don't exist free, floating around. They're always attached to something. And when you have hydrochloric acid in solution, it breaks apart into and then this associates itself with a water molecule and produces a hydronium. So that's what you were looking at. But for calculation purposes, this works just fine. Okay. So what we saw was a neutralization reaction. So how do we deal with acid-base reactions and there's stoichiometry. Basically, we do the same things before. We write the compounds correctly, the acid written correctly, the base written correctly. Then we put them together, balance the equation, calculate the moles, determine the limiting reactant, and then calculate the product, if that's the question. And if necessary, determine the mass or the volume as the case may be. You know, you can go anywhere. Once you get to moles, then you can go any way the question asks. Now, let me see. Are we going to have one of these? Yes. Next, actually, today we have a lab, 1, 2. The third lab after this one, we're going to do a titration. So what do we mean by titration? Well, titration can mean lots of things, but basically what you're doing is you're taking a known concentration and you're adding an unknown concentration of something, and it's producing a product that is detectable. And when the product gets to a certain point and an indicator tells you that you've got an equal amounts in moles, moles are equal for both of them, then you have what's called an equivalence point. And if you know the equivalence point, you can calculate this concentration based upon the volume added and the known concentration. So you're comparing an unknown to a known. In acid-base terms, let's see, for example, we would have, say we want to standardize sodium hydroxide. We don't know what the concentration is. Okay. The molarity is unknown. So we're going to add that to a known. And actually, rather than use hydrochloric acid, we generally use acetic acid, vinegar. It's very stable over long periods of time. So once it's been standardized, it stays there. So if we know that we have, say, 10 mils of this at a concentration of 1 molar, then 1 times 10 is 10 millimoles. When we get to equivalence, when we've got the same number of millimoles, because there's 1 hydrogen here, 1 hydroxyl, so it's a 1-to-1. Once we get to 10 millimoles here, then we know the reaction is complete. And now all we need to know is the volume. How much volume did we use? Because 10 times 1 is 10 millimoles. Well, 10 times what equals that many millimoles? That's the question. If you have that value, the volume, right? If we know that this is 10 millimoles and the volume is so many milliliters, then we can calculate the molarity of sodium hydroxide. That's a titration. Now, the equivalence point is difficult to determine for large numbers of samples. I mean, it's fairly easy to do if you have a pH meter and you can draw your curve and so forth. We'll do that next semester. But typically what we do is we go to an endpoint, which is an approximation of the equivalence point, based upon, for acid-base reactions, based upon a color change. So we have an indicator. Has anybody heard of phenolphthalein? No. It's an indicator, and it's typically the one we use for these reactions. There are a whole host of them that work for different reactions, but we use phenolphthalein. And it goes from acid solutions, it's clear. And when it starts to turn basic, right, just past this equivalence point, it turns pink. So when it does that color change, you know to stop titrating and measure the volume. Okay. All right. For the titration of sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid to reach the endpoint? All right, so we need an equation. We've got the compounds there, they gave them to us. We need a reaction equation. H2SO4 is our acid, right? There's the proof. And sodium hydroxide is the base. There's our proof. So what's going to happen? Well, that cation and that anion get together. That's not correct though, is it? +1 -2. Yeah. And we look it up and it's aqueous solution. And then this hydrogen gets together with that hydroxyl, it makes a water. And that's a pure liquid. Okay, now we have to balance. Right? We need 2 sodiums. Right? Rather than put up the budget, these balance really easy. We got 2 sodiums now on both sides. Now we have 2 hydroxyls. We have 1 sulfate. That's good. We have 2 hydroxyls and 2 hydrogens. So we have 2 hydrogens and 2 hydroxyls get together. And that makes 2 waters. Okay. So now we have a balanced equation. All right, what are the conditions? 1 liter of 0.5 molar sulfuric. So we have 1 liter of 0.5. How many zeros after that thing? 2 of them. And what we want to know is how many moles of sodium hydroxide does it take? Okay. How many moles do we have here to begin with? In this case, 0.5 times 1 is 0.5 00 moles of H2SO4. We want to convert that to moles of sodium hydroxide. I left out the moles part. So for every 2 of these, you need 1 of those. So 2 times that equals 1 mole of sodium hydroxide. That's what you need to neutralize a half a mole, 1 liter of half molar sulfuric acid. Okay. All right. So now that I got you thinking acids, bases, I'm going to give you whiplash. I'm going to leave that behind and go to redox reactions. So redox reaction is, redox is short for oxidation reduction. And electrons are transferred in these reactions. Reduction means gain of electrons. And oxidation equals loss of electrons. If you need to remember what there's an acronym. Oil rig. Oxidation is loss. Reduction is gain. Okay. So, oxidation reductions are one of those major headings that we looked at earlier. And there are other reactions that can be classified underneath them. Oxidation reduction reactions can also include, and we say redox because it sounds better than ox-red. Redox reactions can be combustion reactions. Those are oxidation reduction reactions. Element to compound. If you have an element on one side of the arrow, the compound, it's in a compound on the other side, that's definitely oxidation reduction. Or if it's an element on the product side and it came from a compound on the reactant side, same thing. Those are always oxidation reduction reactions. Lots of other reactions. We have to use oxidation states. And let me see. Yeah, we are going to do that. So if we have sodium and chlorine together, solid, chlorine together, we know we get sodium chloride, solid. And let's see, we need, two of these and two of these. So for each individual atom, what happens? Well, this is a metal. It likes to lose electrons. So it becomes a plus by transferring an electron to chlorine, which becomes a minus. So two pluses make two minuses. And in the compound, we have those charges. So we know that electrons were transferred in the process. And lots of energy generated. Okay. If we don't have this situation, how do we know that we have an oxidation reduction reaction? We have to use oxidation states. An oxidation state is a bookkeeping method. Sometimes it actually signifies the charge on the ion. But if you're in a covalent compound, there are no charges, right? They're sharing electrons. So in that case, we're just using it as a bookkeeping scheme to follow the electrons. So here are the rules. Oxidation state of an atom in an element equals 0. So any of these, say sodium, hydrogen, well, I don't know, pick one. Fluorine. Their oxidation states are all 0, right? Elements. The oxidation state of a monatomic ion is the charge. So if we make an ion out of this, its oxidation state is +1. Or if we make an ion out of this one, its oxidation state is -1. Okay, those are the easy ones. The reason we need these rules is because so many of the elements that are in a compound can be variable. And we got to nail some of them down so that we can calculate the others. So oxygen, when it's in a covalent compound, is taken as -2. So if we have water, we're going to say that's -2. And we haven't identified hydrogen as number 4. It should be +1. Right? So how do we know? Well, 1 times -2 is a -2, correct? And 2 times a +1 is a +2. Put them together, 0. That's rule number 7. The sum of the oxidation states for a neutral compound must be 0. Fluorine is always -1 when it's in a compound. Hydrogen, oh, let's go back to oxygen. Oxygen is -2 in this case when there's just an oxygen by itself. If you have a peroxide, like in your medicine cabinet, the hydrogen peroxide, each one of those oxygens is a -1. Why? Because it's like this, that. So this whole group has to balance these 2 pluses. That means this is a 2- total. That means each one is a -1. So for peroxides, oxygens are -1. Like I said, it's a bookkeeping scheme. So we can't do it any other way. Not if we stick to our own rules. All right. Hydrogen +1, fluorine's -1. Sum of the oxidation states is 0. Oh. For polyatomic ions, let's see, the sum 6, excuse me, I said 7, it's 6. Sum of the oxidation states is 0 in neutral compounds. Sum of the oxidation states equals the charge of the ion in polyatomic ions. I should have plugged in polyatomic there. So if we had, say, nitrate, right? The sum of the oxidation states must be -1. So oxygen, we've already said, is -2 times the 3 is -6, correct? Total. So nitrogen's only 1 by itself. So what must its oxidation state be to balance that -6 so that we still have a -1? +5. That way, -1 is preserved. Okay. All right, let's see, we got any more rules? No, we just get examples now. I'm starting to run out of time. How many more slides do I have? We're close. I might finish before Katie gets here. Okay, let's try this one. Potassium dichromate. Right? Yep. Well, if you got the polyatomics memorized, you know dichromate is -2. So we could work it that way. We could say, just work it from -2. But let's do it for the whole compound. All right. So potassium, wait a minute. No, I left a rule out. Alkali metals, right? The alkali metals are always +1. That means this one is a +1. This one's -2. So now we can calculate the chromate, the chromium. So 2 times a +2, +1 times 2 is a +2. 7 times -2 is -14. So let's see how many we got to balance with those chromiums. -12, correct? So this has to be +12 total, but there are 2 of them. So each one would be +6. Okay. Here we go. Now we got carbonate, polyatomic ion. Right? 3 times 2 minus is -6. And we need to hold 2 minuses out for that charge. So really, we only need to balance a -4. So this would be a +4. Now prove it to yourself. A +4 and a -6 is -2. Okay. Manganese 4 oxide. Okay. -2, -4 there. Right? It's a neutral compound. So this has to be a +4. See, I'm getting behind on my animations here. There we go. PCl5. Okay. We didn't create a rule for chlorine. We did for fluorine. Fluorine's always -1. When you're stuck with a choice and you got a halogen with something else and you don't know what the something else oxidation state is, assume that this is a -1. After all, it's just a bookkeeping scheme. So if we say this one is like the other halogens, -1, then we have a -5 and this is a +5. If we don't do that, then we're stuck. We can't go anywhere. Now, there are times when the chlorines are going to be different values. And that's, if you look in your periodic table at the back of your useful information, you'll find in each square a list of numbers. The top number is the ion charge, typical ion charge. And sometimes the second and third one for the metals. But for the nonmetals, those other values are simply oxidation states for the compounds that they're in. All right, so we got that one. And SF4 would be easy because we do have a rule for fluorine, right? So -4 total, that has to be a +4. Okay, so all I can say is practice. Gets easier with time. Okay, redox characteristics. They transfer electrons. They can form ions. They don't always have to, but they can form ions. And oxidation, again, is loss of electrons. All right, got another term in there. I'm not going to hammer this one too hard just yet, unless it shows up on your crossword puzzle. Maybe that's a good reason to talk about it. So if we have something that, just generically, if we transfer an electron here like that, right? This one is oxidized, right? Because it lost electron. And this one is reduced because it gained electrons. Well, the transfer, the loss, and the gain always occur together. They're never separated. If you got one, you've got the other. Always. So if this one's oxidized, what did it do for that one? It was the reducing agent. It was the cause of the reduction for that species. That means that this one is the oxidizing agent. The easiest way to think about that is oxidizing agents are always reduced, and reducing agents are always oxidized. That gets me out of a lot of jams. All right. Okay. Which of these is oxidation reduction? And identify the oxidizing agent, the reducing agent. Well, the first one is easy, right? Because it's got a metal, a zinc metal on the reactant side, and it's in a compound on the product side. So let's see, I don't have it animated. So if we have zinc on this side plus 2 hydrochloric acid, I'm going to leave out the phases here just for convenience. We know this one's 0 because it's an element, and we know this one's 0. But in here, it's +1. And that makes this one -1. And here, if this is -1, that makes this +2. So I like to draw tie lines. So if we go from this zinc to that zinc, what happened? It was a loss of 2 electrons for each zinc. And there was only one of them. So a total loss of 2 electrons. And the chlorine stays the same on both sides. So the hydrogen is the species of interest. This goes from +1 to a 0. It had to gain 1 electron per hydrogen, right? But there are 2 hydrogens. So there was a gain of 2 electrons. And that's always the case. The number of electrons lost has to equal the number of electrons gained. Now to answer the question, this is an oxidation reduction reaction. We knew that from the beginning because that's an element and that's a compound. But which one is the oxidizing agent? It's the one reduced. This one's reduced, that makes it the oxidizing agent. That means this one has to be the reducing agent. Okay. For B, we don't have time to go into detail with that one, but if you do the oxidation states for each one of those species, you find that nothing changed, right? B is not a redox reaction. Now, the second one is definitely because we have an element on one side that started in a compound. Right, so we have two CuCl, and it goes to a CuCl2 plus Cu, right? Notice we only got one compound on that side, and we end up with two products. Well, actually, we've got two of them over here. So we could write this just as easily like this, correct? Okay. So one of these coppers goes one direction and the other copper goes the other direction. See, this copper goes to here, and that's a -1. This has to be a +1. This is a -1. This has to be a +2. So this was a loss of 1 electron per copper. And this one went over here. This one's 0, and this one is +1. So this one had to be gained 1 electron per copper. So we lost 1, we gained 1. The lost one, the one that was oxidized is the reducing agent, and the one that gained, the reduced one, is the oxidizing agent. This is a special type of reaction called, big word, disproportionation. Disproportionation. It goes both ways. And all you have to do is heat it up. Just get it hot. Smelters do this all the time. They take copper chlorides and heat them up, and they get this as a byproduct, but they do get copper out of it. Okay. All right. So when we balance oxidation reduction reactions, they're a little bit different. We do have to write the unbalanced equation, right? You have to write your compounds correctly. And then you determine the oxidation states on each of the elements. And then use those tie lines to tell you in an unbalanced equation how many electrons move from here to here. So that means that your compounds must be written correctly. And then when you have the tie lines done, you can see how many electrons moved for the oxidation step and how many for the reduction step. Then you balance for electrons. You want to have the same number of electrons oxidizing as reducing. And then if you need to, go back to your budget from that point and finish the balancing. But sometimes the oxidation step will get you there. All right. So balance the reaction between solid zinc and hydrochloric acid to produce aqueous zinc 2 chloride and hydrogen gas. So there we are given products. We have a zinc solid plus hydrochloric acid, means it has to be an aqueous solution, yields zinc 2 chloride. So if this is a 2+ and chloride's -1, we need 2 of them. And they're soluble, and then hydrogen gas. Okay. Oxidation state for that one is 0. For this one is 0. This one's a -1. This one's a +1. We're told that this one's a 2+, and that's -1. Okay. So this is one of those simple ones that you could balance by the budget method. But to demonstrate the problem, if we go from this zinc to that zinc, that's a loss of 2 electrons per zinc. And this hydrogen goes from +1 to 0. So it had to gain 1 electron per hydrogen. But there are 2 hydrogens over there. We already know that. So that means, as a first step, we need 2 hydrogens here. Right? So that's times 2 equals 2 electrons. All right. 2 electrons here say that we've already balanced the 2 electrons right there and there. Right. Well, let's look and see, make sure that the atoms balance too. Well, there's only 1 zinc here and 1 zinc here. So yeah, they balance. Let's check it out just to be sure. 2 hydrogens, 2 chlorines. So that's balanced. We just needed 1 coefficient to finish off the equation. And this is the animation. Now, other ones can get more complicated than this. This is just an introductory method. Okay. All right, that's it. We're done with chapter 4.